Okay, on floor started the recording. So, hello again, everyone. I'm sorry for the slight delay, but now we will finally start with OSC number 14 on 3D image and video coding. Our presenter is Professor Touradj Ebrahimi, and the presentation can start now.
Hello, do you hear me?
Yes, now.
Okay, I think that there is a network or some technical problem because the system, I use it regularly, and today there is something wrong with it. Anyway, so yeah, thank you for bearing with me until we set up the thing that was not working, but hopefully in the next hour you're gonna be compensated by listening to something useful for you. And this is going to be about 3D image and video coding. Now, maybe before just starting anything, let me remind you that 3D is actually one of the many existing and past modalities that tend to bring greater realism into communication. There has been, of course, others. We started as far as visual information is concerned with black and white pictures. We turned into black and white film, and then later on black and white TV. Of course, all of them, they became color at some point. And when things became digital, we even moved to higher and higher resolution. Some of it, of course, happened even in analog, like the high definition. So these are all tending to bring more realism. And some of the things that are happening, like high frame rate and high dynamic range and wide color gamut, are following the same trend. In fact, we are trying to make things better and better in terms of their information content and have greater realism. And the very recent one is, of course, the interest in omnidirectional and 360 that is picking up. And of course, in the past, 3D has been one of them, and maybe still is a potential for the future, because the world we see around us and the information we send to our visual cortex, in fact, is more than just 2D. It has some hints and cues that gives us the 3D. Now, before, again, going to the gist of the topic, I want to add a few more things. One is that always keep in mind that in any of these modalities, and 3D, of course, is one of them too, there are a number of key factors that have to be fulfilled in order to have a successful outcome. And one is always technology. Technology should be affordable, of course, and feasible and easy to use and widespread. And the technology should allow us to not only visualize, but also process the content, edit the content, code it, compress it, etc. Of course, we need also content, right? And this content should be compelling, and it should allow creation of an ecosystem. And last but not least, and this is what most of you have selected to do as topic of research, is to ensure a rich user experience. And often this rich user experience goes to better quality of experience. So 3D is not an exception. Every modality, and it does even limit to visual, has to really have at least these three factors. Of course, there are others too. There must be good business models that makes things sustainable, all sorts of things other than these. But these three, I think, technically speaking, at least, are extremely essential in the success of any modality, and in this case in 3D. Now, in fact, history of 3D is much longer than you may think. It's nothing recent. In fact, it even predates photography itself. Photography, give and take it, depending on who you would consider as the inventor of the first photography machine or first picture, goes back anything between 120 to 150 years ago. But in fact, the stereoscopy, that was one of the ways to create and to trick the brain to see depth, was invented even before any photography was made. You would wonder, but then what were they showing? Well, they were showing hand drawings and painted content. And the idea was very simple. In fact, until very recently, you could go and buy pictures with some device that you would put on your head with two binoculars, and each of the pictures was being seen with one of the lenses, and this would give you the impression of 3D. And this actually invention is extremely old. It goes back to the middle of the 19th century. And when photography was invented, it of course found its way there too. When cinema was invented, it found its way there too. And in fact, at some point, when television was invented in around 1950s, and to be correct, 1952, cinema was so, movie industry was so threatened by television that it actually tried to do something that the television cannot offer, and that was 3D. It lasted for a while, and it died. And then these waves came back and forth until the last wave that some of you, I'm sure, remember, around the beginning of 2000, we started seeing again in cinema, especially, movies in 3D, and this has been actually a big wave that lasted a while. Still, there are some things that are happening, especially in movie theaters, but all sorts of movies and all sorts of music and all sorts of documentaries and all sorts of sports events have been actually broadcast in the past, or at least recorded and then shown also, not exclusively, but also in 3D. Now, we can debate why at home we don't have 3D. The reason is, in fact, is very simple, because it's very difficult to create 3D that is compelling and natural and rich in terms of quality of experience in uncontrolled environments. And uncontrolled environments, typically, when you have a TV set at home, you are in an uncontrolled environment. People's living rooms and rooms are very different from each other. People watch these monitors, these television sets at different distances. The sizes of them are even different. There are all sorts of illumination changes that can happen. Things that you don't see as much changing, for instance, in a movie theater. In a movie theater, you have more or less an idea about what is the size. It can vary, but not as drastically as a television set does at home. Usually the room is dark, so you don't have all these other external influences, and even the distance is reasonably predictable. That's why you see still 3D to some extent still surviving in movie theaters, but not at home, although it wasn't because devices to capture, devices to display did not exist. Lots of these things existed even for consumers. So to really understand 3D, we really need to first understand how 3D is perceived. So I'm going to walk you very quickly, before talking about coding of 3D, very quickly walk you through what are actually the cues, what are the information that is used and captured by your visual organs in order to perceive depth information. Now, on one hand, you have mechanisms that only need one eye, and on the other hand, they need both of the eyes. So this we refer to as binocular and as monocular. Then you have another separation, and this separation is whether the scene is static or it is moving. So that gives us motion-based or motion parallax versus static or pictorial cues of the information that will then inform your brain what is the information of the depth. Then another, actually a little bit less maybe trivial, less easy way to understand the mechanism of seeing depth is how you actually rely either on the content itself, so the visual content itself, or you actually rely on information you receive from various organs, for instance, your eyes or your lenses or your iris, etc. And these are the things that actually help you to actually perceive depth. So this is, the content doesn't really change, but using your visual organs, you try actually to change their setup so that you can actually get some information about the depth of the scene. So these are usually called oculomotor because you really do something. It's almost like a active vision in computer vision, in which you have to accommodate, for instance. Typically, when we look at this scene, we focus on a specific object, and then our eye lenses and the iris and the crystalline, all these things, they try to actually set themselves up so that you can, for instance, if you're looking at a specific object, that object is in focus. Exactly the same way you set up a camera so that it is in focus on the object you want to capture. Of course, there is the question of convergence because we have often two eyes, so our eyes, they usually try to cross each other on the object that is of interest for us. And we have the problem of meiosis, which is the size of our pupil that is going to let us not only more or less light getting into our retina, but also change through this mechanism, we also change the depth of field. And that allows us to see some specific object in focus, but then the objects that are around it, either closer or farther, you could actually modulate how, by making this change of the size of the pupil, you can actually decide how fast or how slowly things go out of focus. And of course, if they go very fast out of focus, you are much more precise in guessing what is the depth of the object that you are interested in and you are focusing in. Whereas if it is slower, it's more difficult. So let me go and really list these again in a more let's say systematic way. So the oculomotor cues, they basically give us absolute depth cues based on changes of something in our visual system, right? So the muscles of the eye, for instance, in order to focus on objects, and accommodation, convergence, and meiosis are three good examples of this. Then you have these monocular cues, as I said, that basically give us, based on some semantic often information, relative depth of objects. It's either their size or their perspective or how they occlude each other or how shadows and illumination looks like and how gradients change that give you this kind of information. Then you have, and this is in fact the origin of the success of the stereoscopic devices, is the binocular vision. And the binocular vision basically is based on a very simple principle that left and eye, right, see a slightly different a given object, and this slight difference, actually our brain is very, very good in turning it into depth. And last but not least is this motion parallax. Objects that are close to you move faster on your retina than objects that are far from you, from your eyes. And this also gives us a lot, actually, of information. Now, they don't need necessarily to move. You could even look at the static scene, and if you move your head, the same thing happens, right? What is important is that the image on your retina moves. It's either the object that is moving or your head is moving that is going to move the object on retina. And the same happens, right? If you move your head, objects that are closer to you move longer distance than if they are farther from you. And in fact, what is interesting, and I guess this is going to be enough for our discussion today about 3D perception. Each of these different mechanisms, they operate in different, actually, distances. So typically, everything that is based on accommodation, for instance, is for near vision. So objects that are very close to you, in less than a meter, definitely. In fact, in the order of tens of centimeters. Binocular is, let's say, mid-range. It can get close as maybe half a meter, not closer, unfortunately. And it can go all the way to few tens of meters. Pictorial cues are often much longer range because you really analyze the content. So it can go all the way theoretically to infinity. It can theoretically even go to as close as you can even see. Although when you get too close, the vision, actually the close vision, is going to be very difficult because it actually gets dominated by echo domination. And then motion parallax. Motion parallax also actually has a very, very long range in terms of informing your brain how 3D is perceived. It can theoretically go to infinity, but when you go too far, then the displacement of the objects in your retina, even if they move or if you move your head, is so small that sometimes it's very hard to detect, and sometimes you cannot even detect it. So, of course, beyond some reasonable distance, you could call, I don't know, 100, 150 meters, 200 meters, and farther, you probably don't have any 3D information, and everything probably will look flat to you as far as motion parallax is concerned. Then, of course, your pictorial cue is going to help you. If you have a mountain that is very far from you, and another mountain that is even farther, if this first mountain is occluding the second mountain, then you know that it is in front of it. So you don't necessarily have that information from any other cues, only you have it by analyzing really the scene and the pictorial content of it. All right. Now, of course, the perception is the very last stage, often, when you have humans as the end of the chain of the 3D processing. But then there are other things, right? You need to understand also capture, because if you don't understand capture, it's very, very difficult to know how 3D actually is being perceived, because if the way you capture can have an impact on it. And in between capture and consumption or observation, there are lots of things, right? You have the display itself that can have a very, very important role, the rendering or visual optimization for that display that can have a very, very important role, and of course, coding, decoding, and transmission, and eventually even protecting some of the information in case of transmission errors are part of this whole thing. Now, I'm going to start again by asking ourselves, what is really meant by 3D? Because although everybody talks about 3D, 3D doesn't mean the same to different people. Everything I told you about the history of 3D until, in fact, a few years ago, including the last wave of 3D cinema, defines 3D really as the stereoscopic 3D. In fact, to be really correct, one has to call it S3D, and some people do it in that. This means that the capture is always done using at least two cameras, the same way our eyes perceive the environment. And then the display also manages to send each of these two pictures into your correct eye, and then the rest is taken over by your perception and all the cues I told you about. But of course, you can create 3D otherwise, right? You could have multi-view. Why should we limit ourselves to only two cameras? There are actually animals, they have more than two eyes, and they have very good depth perception. Many insects are actually like this. So there we talk about multi-view. So multi-view is just a very trivial extrapolation sometimes of stereo. So instead of only two, you have more than two. Sometimes it's even more complicated. They can be even configured in very different ways. They do not need to be next to each other like the eyes is. One can be on one side of the room, one can be on the other, and then the two others in some two other places. But of course, it doesn't prevent that you also put them next to each other and make a array of multi-view. And it doesn't even need to be a 1D array, right? It could be 2D array. It could be like a matrix of capture devices. Another thing that can also help you to define 3D, and sometimes people actually define 3D like this, is that you basically have two capture, or maybe more even sometimes than two capture devices. One of them does what a 2D capture device does. It's like a camera or a video camera that does just conventional video or image photography. And then you add to it another capture device that actually gives you the distance of the objects from this capture device. And then you manage to somehow synchronize the two and calibrate the two so that for every pixel, more or less, that you capture with your conventional camera, you can also know what is its distance. And that obviously gives you also the 3D. This is, note that this is not how we actually perceive, right? We don't really have in our perception system, we haven't adopted a system where actually we explicitly capture the depth by a sensor. We actually use all these other cues to guess them and to estimate them. You could of course do that also differently. You can instead of having a depth sensor, you could actually, especially this is very popular for synthetic 3D. You could create surfaces. I can actually mathematically define a sphere. I can mathematically define a cube. I can mathematically define even more complex surfaces using meshes or other type of parametric representation of the surface, and then match on it, add to it texture, and then this texture that is mapped on this surface is going to give me the impression of the 3D. Now, more recently, and these are the ones I have put in red, people are actually trying out other ways of defining 3D. Now, not that they are, again, very recent, they maybe are not as old as stroboscopic, but they really, all of them, they go a few decades back. One of them is light field, one of them is point cloud, and one of them is holography. Light field, I'm going to tell you a little bit more about that. You have heard that many times in also, I know, in other talks that you have heard. I'm not going to spend too much on it, but more talk about how it is coded. Point cloud is basically, in a way to have the depth plus texture realized. So it's a different way of doing it. Point cloud does not necessarily, although it can be, is captured directly. You could, but you could also analyze a content, even a movie, which is in mono, track some interesting feature points in it, and then create from motion depth from motion, what is their position, and then the 3 position of these points, and the texture gives us the point. Holography, of course, everybody knows. Holography is a completely different way of looking at the visual information in a complex space with the real and imaginary part, and usually the real part conveys the amplitude, or actually the amplitude of the complex value gives you the amplitude, and then the modulation is given to you by the face, or the face of the complex value. It's a completely different way of looking at things. You need, of course, a source in order to modulate your objects and get back to you reflections, and then you need ways to capture this, and then you have to basically do the dual process in order to turn this modulated reflected light into a 3D object. Now, I want to first start with the easier ones and tell you, because historically they have been around for a longer time, how actually these things, the 3D, according to these easier ways, is represented. Now, representation is always the prerequisite and the background of coding. If you don't have a mathematical representation of how your content is represented, coding it doesn't mean much. So you really have always, either explicitly or implicitly, some sort of representation of your content. This doesn't need necessarily to be 3D. It could be visual, it could be even audio, or anything, actually. Any type of information, you have to have first a definition of how you want to represent it. A digital picture, for instance, you say it's made of a few points that bear colors, and this is called a pixel. That's our representation, and then we try to code it in the most efficient way, compress it if we can. So in 3D, the 4 first mechanisms that I told you that are a little bit older are actually being represented in the ways now I'm going to tell you. The stereoscopic is very, very simple. It is represented either with 2 images, left, right, or you could even decide you want to have the left, right ordered differently, top down, so it doesn't really matter, right? You could put them in a picture, and you have half of the picture, either the top one or the left one or the right one or the bottom one of the views of the stereo, and the other one is the other. You could make it a little bit more convoluted by, for instance, even making use of interlacing. You could have one line of your representation to be one of the views, and the next line the other view, and then go back and forth and create this interlaced effect. So these are basically the representations that are and have been adopted in stereoscopic so far. You have also in depth plus texture representation that is reasonably trivial. Texture is usually just an image, so it's basically a 2D image, so a bunch of pixels often. And depth actually is also often represented as an image, just that the values of the pixels are how far that corresponding pixel is from you. And then you have a 1 by 1, right? So if you look at the same pixel on the image, it tells you what is the texture. If you look at that same pixel in its depth information, it tells you how far it is from the camera that captured it. Multiview, which is this extension of stereoscopic, is also in fact just increasing. So you could actually increase the number of the views, go from 2 to something else. In the example I'm showing you on the slides, we have adopted 9 of these views. Why not? But it could actually be even combined with the depth plus texture. So multi-view, most people may think it is always represented as a stereoscopic, just that instead of 2 we have n, but actually it's not necessarily the only way. Some people do this, but you can also have it, a multi-view can be depth plus texture when you have more than just one depth and one texture. You could have several depth and several textures of many capture devices that are organized according to the configuration and give you the information. Of course, there's going to be a lot of redundancy, but not necessarily only redundancy. So you cannot, for one view, necessarily perfectly have the other view of them, right? Because there are things you cannot even predict, like how the illumination changes in the room if you don't really go and see it in realistic environments. Then the last one, this one is quite self-explanatory. The surface or mesh plus texture is represented usually by some ways that you represent the surface. Mesh is the most popular one, but not the only one. You could in fact have even parametric surfaces, saying, I don't know, a cone or a sphere or a plane or a combination of these, and then the texture is usually just an image that you really map on this texture by defining points on the texture corresponding to points on the mesh, and everything in between is stretched as if this texture was a rubber, was drawn on a rubber surface, and you basically try to wrap it around the surface that you have defined. These are the representation models. The question is, how do people code them? So let's start easy with 3D. Now, 3D images, sorry, with images. So the images actually, there are many ways you could, of course, represent any of these, code any of these representations. I'm not going to cover all of them because there are zillions of them, and many of them are actually just exotic and academic. I'm going to concentrate only on the methods that are being used, and often methods that are being used are according to a given standard. And in fact, the most popular standard currently for still images, as you know, is JPEG. So in fact, you would imagine there must be some extensions of the JPEG in order to cope with 3D images. Now, I'm going to surprise you, although it is true and your expectation is correct. JPEG committee itself was never too hot about standardizing the stereoscopic or a 3D image format. We can again debate why is that this never happened. Well, the main reason is because JPEG committee, the first priority it always has is very high quality and very high quality of experience. Very high quality of pictures, very high quality of experience. And it was very clear that none of the even most recent cameras that would take pictures and even taking video, they were really giving a reasonable or something you would actually call a robust quality of experience. So JPEG itself never standardized anything. For still pictures, JPEG did not, but others did. So there are a couple of de facto standards. One of them, MPO, is actually, it's a standardization body, but it's at the national level that did this. And the other one is just proposed by some people, and other people have just taken them. None of them is extremely popular, but one is called JPEG file format. So this is basically a JPEG in which the way I told you, you define left, right, and you actually have two pictures in your file. One of them is the left, one of them is the right. And if you put the .jps as extension, then although it is JPEG format, people know it is an image that has two parts, and one of them is basically one view of a stereoscopic pair, the other one is the other. MPO, which is a multiple picture object file format, in fact, it was originally designed to put many pictures inside one file. And often the format, the compression applied to each of the pictures is JPEG. It has been used also for stereoscopic. In fact, this one is even more popular than JPS. Although JPS says explicitly stereoscopic, MPO is more popular. And the idea is the same. So you basically have two pictures in this case. If you had even more, you could have put more, and you put them inside the very same file. The compression algorithm used to compress it is JPEG, but the way the file format has been created is slightly different from the way JPEG standard is, or those who use JPEG standard. Maybe one thing that I didn't know where to put, I still tell you, is that of course you go to Cinema and you know that Cinema is based on JPEG 2000 format. Although JPEG 2000 was for video, well, for images, it is used for video in this case, for reasons, again, out of the scope of this discussion. But of course, when Cinema became 3D, it was already more or less digital. So the DCI, the Digital Cinema Initiative, actually also defined a stereoscopic JPEG 2000. Again, this is not something that is necessarily endorsed by JPEG 2000 because JPEG committee didn't want to really make a standard that wouldn't have the highest level of the quality of experience and quality of picture, but other people have done it. So it's very in fact not that rare that some other consortia or some other industry groups or some other company, they just take a standard and then they add to it something. It's not anymore a standard according to the definition of the original one, but it becomes, if it is successful, a de facto standard. Sometimes they go back to the standardization, they standardize it. In this case, they did. What about video? So video, you can imagine, there is far more, because there is a lot of actually activity around video in general, because you can do all sorts of things with video that you cannot do necessarily with images, which are simpler objects. Now, of course, one way, very trivial way of having 3D video is just consider the stereoscopic pair of, if it is stereoscopic, left and right, as two videos, as two different videos, and then code each of them separately with a codec that is designed for each of them, and then you find ways to stream them and synchronize them, and then you basically, when your times comes to display them, you make sure that the two streams are ready and in sync for exactly the same frames that have been coded. This is not easy, in fact, because as you can imagine, compression of video has more complexity than meets the eyes. In fact, if you have especially a constant bitrate channel, or you want to have a constant bitrate, you usually have a buffer. This buffer can, is usually desynchronized from the order in which images are coming in. So sometimes it takes more time to decode an image, sometimes it takes less time. So all these things, one has to really be very, very careful to to make sure they are synchronized. So there is another way you could do this, and this is called frame compatible. Instead of coming up with very complicated mechanism to synchronize two independent bit streams, each corresponding to a different view, you could actually try to say, hey, why don't I just put them in the same picture or frame, and then I just agree on how to I fit it. Maybe I just say, you know, the frame's size is twice larger horizontally and same size vertically, and then effectively each frame is a left-right frame. You could say it's twice taller, so it's top-down. All these representations I told you. But the interesting thing about doing it this way would be that you don't need to synchronize anything, right? Because you are sure by putting everything in the same frame, you're sure that you are going to decode them also at the same time. So you don't have this problem of synchronization. So frame compatible actually is a popular way people have been coding in the past 3D, and nowadays maybe less, but that's not because the method is not good. It's just that because 3D is not as popular as it used to. Now, there is actually a standard by MPEG just to code the depth. So they say, okay, somehow the texture, you can use just an existing standard, whether it is MPEG standard or not, doesn't even matter. But if you want to code the depth information in the 3D representation depth plus texture, this is how you can do it. The depth information, as I said, it's really like an image often when it is captured, but it doesn't have the same statistics as an image, right? It's not as much texture-y. It doesn't have necessarily the same ranges. It doesn't have the same statistics. So it doesn't necessarily need to be coded the same way as natural content is. And this is exactly what is being done. So there is a simplification in terms of how this depth information is done, so that in fact the results are better. You know, you hate, for instance, seeing ringing effects on depth, right, on the edge of the object. So you know, you can manage to not to have this kind of effects by selecting right way of coding. Then there is the multiview. Again, multiview, you could see it as just a simple extension of simulcast, of stereoscopic, as I told you, or you could see it as an extension plus depth. So you have more than just one texture plus depth, you have more. And if you have 2, 3, 4, 5, 6, doesn't matter, you call them just multi-view plus depth. And that's something you never say about stereoscopic, by the way, right? So you know, if you say something is stereoscopic, you know there's no depth in it. If it's multi-view, you don't know. It can be many more than 2 views, or many more than 2 views plus their corresponding depths for each of them. Now, the multi-view, if you don't have the depth, is currently coded, and there are 2 ways of coding it. One of them is through an extension of H.264, which is called MVC, Multiview Video Coding. And the other one is the same, but it's an extension of HEVC. I'm going to quickly tell you what it is in the next slide. And then if there is depth, then there is something called 3D HEVC. So 3D HEVC, as opposed to MV HEVC, they differentiate from each other in the sense that 3D HEVC considers and assumes that there are many views, but then depth also for each of these views that have been captured and are available and have to be coded. The multi-view, not. So MV HEVC and MVC also, they basically consider that there is no depth information. If there is any depth information, by some processing, you have taken them by comparing the different images and guessing what is the position of the each pixel by making triangulation. So this multi-view coding, maybe it is worth a little bit spending time on. So the idea, the original idea, was that you have more than one camera that is looking at a scene. And then, on the other hand, not necessarily on a non-conventional receiver, but on a receiver that could be even conventional, you see it. And what is given to you as added value is that you could just change from one view to another. You can go from one view to another. Now, the configuration of the cameras doesn't need to be a very nice linear or clean configuration. It could be even more or less randomly scattered around a given scene. You could imagine, for instance, if there is a sport event, every, I don't know, now and then you will have a camera that is looking at the sport event from a different position. They don't need to be even regularly separated or to be all from the same distance of the scene. So in general, multi-view can just be completely random. It could be coming from many surveillance cameras that are looking at the same scene under surveillance. It can be many sport events. And the idea here is that you allow the end user to switch not only between the views, but even in between the views, meaning that you create actually, if you want, even intermediate views, and how you can do that. So now, without entering to the discussion of how you can do these things, because that goes a little bit into computer vision and image processing, the coding of it is by itself also very interesting, because you can imagine that if these cameras are looking at the same scene, regardless whether they are regularly spaced or not, they will have some redundancies, right? So they have the usual expected spatial redundancy and temporal redundancy if it is video, but they will also have interview or within the view redundancies, right? And so you can actually not only reduce the redundancy between the views, between the frames and within every frame, but you can also try to predict one view from another view you have already decoded, and then only send the error of this prediction. Now, how is this done? Can be done in many ways. So I draw your attention to the lower left. So you see here a very simple way, just a stereoscopic pair. So you have on the top one of the views, and on this one is called left view, and on the bottom you have the right view, and then every one of these squares of different colors and with different letters is showing you one of the frames. So you could, for instance, think about coding the first row on the top, which corresponds to the left view, by using just a normal video coding. So the first frame obviously has to be intra-frame, you have no pass, then maybe you jump 2 frames or more, and you predict that one, and then code and send the error of prediction. Then in between the two, you have some B frames, and so forth. But then you don't need to do exactly the same for the second row, which is the right view now, because you know that there is a lot of similarity between them. So you don't want to make multicast. You could have, but you don't want to do multicast. You are going to actually predict, for instance, from the first frame of the left view, the right frame, the right view's first frame. And then you see here an example, not only this way, but you see that everything else actually in the right view is coded as a B frame. Now, you could do that if you have more frames in very different ways. So on the top right, for instance, you have an example in which you have many views, and each of these views are basically being coded completely independently from each other. So this is typically a multicast, but then on the lower right, you have the possibility to actually be even very sophisticated, right? You could even have one of the views, for instance, the Cam 2 view, interpolated between Cam 3 and Cam 1 view. And of course, if you take the temporal dimension into account, it can become very, very complex. Now, these are all possible. In fact, the MPEG standards that allow these kind of things, they have all the syntactic element that basically let the encoder do whatever they want. And the choice on the encoder is only a matter of how well you want to exploit the inter-view redundancy, but how much memory, how much delay, how much computational complexity you can afford. You can imagine some of these can require that you store tens, if not dozens, of frames. Maybe you don't want to do that. It not only creates additional memory requirements, but also can create delays because you cannot decode a given multi-view point if not all the views of that moment have been decoded. So it's enough that one is not, then you don't have that moment. Delay also is an issue. And of course, all the number crunching to do all these things can also have adverse effects. So the standards, of course, usually just tell you this is the syntax and this is how a decoder should use the syntax, and then the rest is left more or less to the choice of the manufacturers, how complex or how simple they want things to be done at the encoder that generates this syntax. There is just an exception. Often standards like to define what is called a profile, which is an upper level of the amount of complexity you can allow or the amount of delay you can allow. That's the only really additional constraint that could actually dictate some constraint and limitations on the way you want to predict views, either temporally or inter-camera from each other. Now, there is another concept that gained popularity a few years back called FTV, Free Viewpoint TV. So the idea here is like a dream. Imagine that you have a drone or you can fly, and you basically can fly inside the scene. If it's a sport event, especially, it's very attractive because then you can look at the sport event by being in place of the player or next to the player, or you could be up in the air where there are no seats, or you can go in one of the seats, or you can put yourself on the corner of the if it's a football match, the football train, and so forth. So that is a dream, right? The same dream, of course, you could realize it also if you want to, for instance, have a possibility to move around an area that is under surveillance without actually moving any camera or having any specific mechanical or motor-based solution. Now, how does this happen, and how can you do this? Well, one way, not the only one, but one way is to say, hey, I'm going to fix the rate, but then I'm not going to say how many really cameras I need to capture the content. I'm not even going to tell you how many different views you need to generate, because you can have infinite number if you want. So I'm going to really try to synthesize a representation from any number of cameras, as long as it's more than 2, and create as many views as I want when I decode it. So the representation should be so flexible that can take any number of views of the scene that I'm capturing and render to me any number, not the same number as the capture, different even, as the number of those views that have been captured. Now, how do you do this? You can do this with this idea of multi-view, but also plus depth. So if you don't have this plus depth, things become very, very complicated. So here on the left of this graph, you see a number of different ways you could capture, right? So you can have a stereo pair that is looking at this scene. You could have a camera that has texture plus depth. You could have multi-cameras, so many of these cameras, and they could also have depth if you want. Or you could even imagine you have a regular content that is captured, and then this content is converted somehow, either manually or semi-automatically or fully automatically to 3D, represented by many views or many views plus their corresponding depth. So here, the corresponding depth that is always shown with the dashed lines on the left. And when it is plain, it means it's just an actual view. So on the left, you see that you can have all sorts of things, right? Then what you do is that you are going to actually code this depth plus texture together by taking as much as possible the redundancies between them out. And then when it comes to render them, you could actually completely select completely different ways of looking at them. So you can look at them only one view, you could look at them in stereo view, you could look at them by having a head tracker that if you move your head knows that, oh, you want to see some other part of the scene, and then changes the perspective. It can do the same for two or more people that would look at the scene, which means that then you certainly need, except if the two are completely on top of one another, you need more than just two views, right? You have to create several virtual views or several views of the scene, and at any point of time, only two of them are being seen by one of the observer or the other, but you don't know which one. So you have to create as many as you can to create a multi-view, this autostereoscopic display, and then one of them sees only two, the other one sees another two, for instance. So just a repetition, I know I told you, so the multi-views, HEVC and the 3D HEVC, these are the two extension I told you of HEVC. Now the difference really between them is the multi-view HEVC is really using always the same tools as HEVC itself is doing, which is B frames, I frames, and P frames basically. Now the motion estimation when it is in between the views is not called motion estimation, it's called disparity estimation, but the idea is the same. And so the only thing really that makes a multi-view extension of HEVC different from HEVC itself is the way the syntax is and the semantics are defined, right? So instead of saying, okay, I decoded now this frame, instead of saying now displayed after the previous frame, you can say, no, this is the same time, but it's next to the other frame. So if you have another view, or you have the possibility to see this view also in your display, well, this is the same moment in the scene from a different perspective. Otherwise, the tools are exactly the same. The hardware is the same, everything is the same. Just the way you control and call each of the frame will be different, and therefore it can be used differently. The 3D HEVC, however, is more complex, right? The 3D HEVC uses a combination of the depth coding and the texture coding that is used in HEVC, and then it creates actually not only a different syntax but also additional tools that will tell us how to code the depth information and how even use this depth information to predict the other view, not only by compensating like HEVC does, using disparity, but actually taking the adaptive information to even predict it better. And then the error, of course, you are hoping will be even less in this case, and you get better pictures. Okay, so let me just more or less summarize for you. In terms of video, so in terms of image, I told you. So image, basically, there is no standard really for any of the stereoscopic, multiview, and depth plus texture, and even the surface plus texture. But in video, there are actually a number of international standards. Now, all of these standards, fortunately, are jointly developed between ITUT and MPEG. So one of them is MVC. So this MVC is actually a joint extension of a joint format H.264 or AVC that was extended as SVC, which was bringing scalability. And more or less the same tools actually in scalability are being used for the MVC. And then for HEVC, which is another more recent joint project, there is a scalable version and it's a scalable version. So more or less using the same syntax, but the semantics are different. And if you have depth, then you have to go and have another additional extension, which is not only changing the syntax, but also keeping the tools the same, but also changing the tools and how compensation and prediction of one view for another one take also into account this depth information. Okay, but let me try to just, this is really what is today. And today, as we talk, there are no other standards really to code 3D. There are, of course, a lot of exotic work that is being done in academia. They are not uninteresting, but I don't think that we don't even have time for it, but we should probably not take any of them out of the lot and just talk about that one. I think this is for all practical purposes. I think the standards are also give you a very, very good understanding of the principles that are used there. But 3D, as I told you, can be created other than just by binocular vision. And one of them is through this motion parallax I told you. So if you remember the slide I showed you, in fact, motion parallax is one of those cues that even covers the largest range, in fact, almost from as close as you can get from using accommodation, so a few centimeters, tens of centimeters, all the way to infinity. Of course, when you go close to the infinity, the impact is less. When you are too close, the impact is less. Which definitely is far larger in terms of cues when you compare it, for instance, to binocular cues. So the idea here is very simple. You have these multi-views. It could be any of the methods I told you. You could even decide to look at it one view at a time. But then when you change your position of the view, if this is a screen that is fixed somewhere and it has a camera that looks at you and sees where you are moving, it's going to change the perspective by putting other views. Or if it is a mobile that is like the cell phones that you have, then you could, or a tablet, then you could actually move that, and using the accelerometer, you could actually change the views. This can be done. In fact, it's a little bit complicated, but I think it's good to show you. So on the left here, you have basically a number of views. Let's say this is how it has been captured. There are only 4 of them, okay? No more than 4, or 5 actually in this example, right? It starts from 0. So 0, 1, 2, 3, 4. And then on the right, all the way on the other side, you have not only 5, but in between you have added another 4. So in fact, every view is multiplied by 5. So you end up having 25 if you make the counting of it, right? So this is how you you can actually turn something of limited number of views to something large, combine it with coding using multiview, and use by estimating the depth and create all these intermediate views. Okay, but things don't stop here. You don't need necessarily only have views. You can actually see the information again completely differently. Again, I don't want to spend too much time in that because I know that at least in Lausanne you had a chance to see some of these things. So you could actually say 3D is just one way of looking at this plenoptic representation of visual information, which is 7-dimensional, right? And you probably remember we said one way to simplifying it is to actually talk about light fields, and in this particular case 4D light field. So you reduce the dimensions from 7 to 4 by making 3 assumptions. One is that the wavelength is constant, so it divided into just wavelengths from R, G, and B, for instance, to create your color. So that's one less dimension. You could say the scene is static; it doesn't change, so that's one less dimension. And the last one is constant intensity along the ray of light. So this is not reducing really a dimension, but effectively it is. It's like looking at a plane in a 3D representation. Well, on the plane you are 2D, right? You can represent every point on the plane with only 2 coordinates. You don't need 3 coordinates. So that's the same here. You get into 4. And there again, the good news is that we know how we can capture these things, right? So we can either capture them by having micro lens arrays or actually an array of cameras, and then our 4D light field can actually be represented either as the image on the right, which is one way of representing it in canonical form, where every pixel is a superpixel that contains all the directions, of course quantized, from any direction emanating from that pixel, which color, for instance. Or you could just turn it and rearrange it so that every one of the images is actually like a view of from a different perspective of the same scene, right? Now, how do you code that? There are many ways you could code that again, right? You could use actually, because this is effectively a multi-view, just that this one, there is a little bit of a spatial relationship between the views. So we know that all the views are at the same time, right? In the previous case, every row were every column was at the same time. Here, everything is at the same time. So you could basically go through them, right? You could go through them and predict them differently. You could also do what some do. In fact, take one of these 4D light fields without time, right? And in fact, consider each of the small images that people call aperture as one frame of a video. So in fact, turn every view, every aperture into a pseudo time. So you could start from the top, go down in a zigzag manner, line by line, and then turn it into a video, and then code it like a normal video. That's the type of things that people do also. And of course, JPEG committee is trying to do the same. The JPEG committee is saying, hey, you know, this is actually a new way of looking at 3D. This one, JPEG committee, is more convinced that it is going to be able to provide a high quality of experience, high quality of picture. So it is standardizing. And what you see here in this slide is actually what is the vision and what should be standardized and what should not be standardized. Let me walk you through this very, very quickly. On the left, you have the light coming in. So it can come out from any direction in the space. And on the right, you have a display that can potentially give you light in any direction, right? And in between, of course, you have to turn this light that is coming from any direction using a device that could be an acquisition device, using an underlying representation into something that, of course, is feasible. But that thing that is feasible is not necessarily the best way to represent the content for coding or compression. That's why in between you need a format conversion. Turn, depending on which kind of acquisition device you have, from the representation that is good for acquisition to a representation that is good for coding. Then you code it, then of course you transmit it, you decode it, but then the representation that you get is a representation that is good for coding. It's not necessarily good for display. Now, it depends, of course, on your display. It doesn't even mean that the display representation should be the same as the acquisition representation. It could be another one, right? Imagine the display is just a 2D display, or a stereoscopic display, or a multi-view display, or a light field display. So they are not using the same representation. So you have to turn the representation that was good for coding, which is on the packaging and decoding, to a representation that is good for that particular display. This is called rendering. Now, what do you standardize here? Definitely not the way the representation acquisition, because you want to leave that open. You don't want to do the representation in display either. You want to leave that also open, because you want to be able to visualize the content in any ways people want in the future with any type of displays, and you want to create the content in any ways people want to acquire it, in as large as possible. So you don't standardize them. You therefore, because representation you don't standardize, you are not going to standardize format conversion on the left, the purple one, and you're not going to standardize rendering on the right, because this is very display dependent. However, the input, the output of format conversion that goes as input to encoder, this has to be standardized, right? That's the representation that is most suitable for coding. So that has to be standardized. Likewise, what is coming out of the decoding has to be also standardized, because that's the same representation. Here it's the same representation. And then, of course, the syntax in between when you transmit or store has to be also standardized. And how, of course, the decoder has to use the syntax to create the representation that is in between rendering and the packaging. Now, in addition to these, of course, you probably need also to standardize a number of metadata that can transit all the way from acquisition to format conversion to encoding, all the way to the display itself. That can be useful. So what is standardized in the view of JPEG Plano is the syntax, obviously, of the coded or stored, transmitted information, the representation that is used for encoding, the representation that is used after decoding, which is the same, the interface with the renderer, the interface to the encoder from the format conversion, and some metadata. Everything else is open. Now, currently, actually, for at least light field, this 4D light field I told you, JPEG has been actually working on a standard. It issued a call. The call was responded to, and some winners and less winners were selected. And currently, this is the block diagram of how it looks like. So on the left, you see it can actually get all sorts of input, right? It can have high density camera array. That basically means that you have an array of cameras that give you the light field representation as multiple apertures. Why is it called not called multi-view? Because multi-view could mean it is not regular, right? Here it's regular. Lenses is the same, just that it's another way of looking at the same thing with optics. So it could be any of the two. It could be also multi-view in the sense of, for instance, 360. It could be a 360 light field, for instance. And it could even have depth sensor. If you have it, great. If you don't have it, you have to come up with depth sensor. So this whole thing goes inside the box, and if there is no sensor, of course, it is sending the depth information for if you want to have it not recalculated again on the decoder, you could send it with depth disparity coding, and it could be even scalable if you want. Then what you do is that inside this multiple views of subaperture, you select a few of the key subapertures. So you don't look at it, as I told you, like a pseudo-temporal sequence, but you are going to say, I'm going to select a few keyframes in there, and I code them. And then everything else in between, I'm going to predict. Now, exactly how the position of this keyframe should be, it's an encoder's matter. And then the rest basically is how to code the error of the prediction. And you could even do it in a scalable way, meaning that you could decide that some of the views you want to give it lower or higher quality because, in fact, I actually didn't mention it even since stereoscopic time. People know that if you give to the brain two views and one of them is lower quality than the other one, in fact, the brain tends to match the higher quality rather than lower quality one. So JPEG Learner is not going to stop there. So it has started with light field, but it is going to look at depth photo and point clouds and even holography. In fact, it is looking at them right now, and it's trying to standardize it. And there is good news that maybe there will be, in fact, not as many modality for representation as one may think. In fact, this graph is showing plenoptic representation of visual information of the same content. On the left, you have two. One is texture, one is depth. In the middle left, you have the point cloud. In the middle right, you have the multi-view, the light field multi-view. It could have been also lenslet if you wanted, if you had to rearrange it differently. And on the right, you have the same thing in holographic representation. Now, the good news is that mathematically, you can actually move from any of these to any of the others. I can turn the one on the left to point cloud. I can turn the point cloud to the one on the left. I could turn point cloud to multi-view to point cloud, and even to holographic formation. So there is a chance that if one does the, for instance, point cloud coding, it's not necessarily the point cloud that you have to code. Maybe it's just enough to turn it first into multi-view and then code that multi-view instead. And you have the tools for it. In fact, this is what is happening in MPEG. Now, this is a little bit of a roadmap of the MPEG in the next, let's say, 4 or 5 years. It has also 2017 in it. In fact, if you look at the middle of this between 2019 and 2020, you see that there is a point cloud compression. So MPEG basically is actually currently busy doing this. And you see that a little bit later on the right, around 2022, it's even doing the light field for video. So the light field for video, maybe it's a little bit far to discuss about, but the point cloud compression for 2019 is much closer. And in fact, work has started there. And currently, the winner technology for point cloud coding, according to studies that have been done in MPEG, is you turn it into multi-view and code it as multi-view. So you don't code it as point cloud. So this shows that this vision of JPEG Plano at least is also confirmed, and there is a chance it can come up with some results. Okay, so it's a little bit over an hour. I've been talking. I'm getting tired really, so maybe we just stop here. I think this is also my last slide. So maybe time for questions if you have any.
Thank you very much for the talk, and now everyone is free to ask questions via the chat box on the left.
Okay, so
yeah, hello, can you hear me? This is Bernard. Thank you very much for the talk. It was very interesting, I think. So even for the early topics, so I knew a bit, but also these new findings and work ongoing is very interesting. And I just have this last slide in before me. So I was wondering, this immersive video coding, what this could be. Do you have an idea? Could you explain what is meant with immersive video coding?
yeah, so so you see that. Let me actually go a little bit before that. So you see that on the system and tools, you see something called omnidirectional media format, right? You see it?
Yeah. Yeah. OMAF.
So exactly, OMAF, exactly. So OMAF is purely currently a system issue, meaning that what you do, it tells you, hey, if you have a 360 content, take this 360 content, project it into a rectangular frame, then use HEVC. That's how it is. And then on the decoder, it says, hey, if you decode something and it says, I'm an OMAF, do the opposite. Project it back into a sphere, and then you can, for instance, look at it in a head-mounted display. Now, of course, there's going to be a first version of that and a second version of that. And now what will happen is that even in the second version, the idea will be still the same, that you convert from a sphere your 360 or omnidirectional content into a rectangle and decode it. But nothing would prevent you. Why should you do this? You could actually start coding the information on a sphere. So the new and immersive video coding, the red one that you asked, that is coming after point cloud, is a placeholder for a different way of coding 360 information. So not first flatten it and then code that flattened information, because we know that there are some areas that will be stretched, some areas that will be the opposite, and so you lose quality. So the idea here is that you do your motion estimation, your transformation, your quantization, all these things. You are going to do them in a more appropriate way on the sphere and not on the plane. That's the idea. And of course, then it will feed into immersive media AF, which is even yet another extension of OMAP, but this time it's not called O, it's called immersive, right? That can even include the light field in it.
Oh yeah, okay, thanks. So this gives me at least some hints in which direction it goes. Thanks.
We have one more question in the chat. Werner asks, are you aware of any further standardization activities regarding subjective test methods for 3D?
Yes. So IEEE actually has initiated quite a few. Now, a few years ago, IEEE initiated, but you should know that, the P3333 dot something, right? And this one is to actually try to evaluate quality of 3D, but not only saying how good or bad it is, but saying how much is the amount of discomfort, how well you see the depth, all these things, all these additional dimensions. So there is a work that has started. In fact, in QoE-Net, our partner in Korea is heading that activity, and probably you should be aware of what they are. Now, except that, there is also another IEEE standardization that started more recently. This one is about really looking systematically how quality should be evaluated on an immersive environment. So these are standards. So basically, part of the standard is about agreeing on what we mean by immersive. What is it? Like, is a 3D head-mounted display should be called differently than a 2D version of it? Is a light field head-mounted display should be called differently? So try to even the nomenclature put an order. And then some of it is about how to come up with influencing factors. So what are the influencing factors? Some of it is about what are the best guidelines. Some of it is about what are the best codecs to use in which situation. Of course, they rely, for instance, for coding, they're not going to invent new coding. They're going to probably propose some of the coding that MPEG and JPEG are doing, or maybe some other people. If AOM becomes successful with AV1, probably AV1 also will have a stereoscopic and multi-view and light field and things like that also associated with it. So these IEEE, there is this IEEE, I don't remember the number, but probably I can communicate that to you if you are interested in knowing more about that.
Yeah, thanks. I realized I could talk as well. Yeah, I was aware of the P3333. We had that as a deliverable as well. That was a while ago. But you don't. If you could just send me the name of the working group or the work item that you just explained, that would be great.
Yeah. Okay. Remind me by an email. I will do it.
Do you have any further questions? Currently, it does not look like it. Well then, let me thank you again for the presentation, and then I will close this OSC 14.